Hi, everyone. My name is Minghao Zhang, and I am a first-year PhD student with Dr. Chris Rogers at WBIC. And here I'm going to talk a little bit about the basic concepts of the parallel transmission technologies at 7T and a few examples of what we can already do in Cambridge. Okay, I'll just scroll through, sorry. So why do we want to image at 70 or above? So we are obviously trying to take advantage of the increased SNR at higher field because SNR is proportional to the field strength. And with the appropriate choice of a pulse sequence, we can trade that SNR to either higher spatial resolution or faster image speed. Another important aspect of a high field is that the relaxation time changes. The T2 star relaxation time I mentioned earlier by AJ decreased from about 45 milliseconds at 3T to about 25 milliseconds at 7T, so that we can image with a greater bolt contrast in fMRI. Now, of course, everything comes with a trade-off. So at higher fields, the biggest problem that we have is the transmit field will become more inhomogeneous, and that's because the Larmor wavelengths become quite comparable to the size of, say, a human head. So this kind of dropout, like very clearly seen here, will often be formed at back of the head or more lower parts of the brain. And this kind of effect is seen in both EPI images here and also in structural images. And another thing to mention is that at higher fields, we usually encounter the problem of SAR, and because the frequency increases, and that means we more easily hit the legal limits of SAR. So that puts some other constraints on our imaging. Now, what comes to say today is the PTX technology, parallel transmission. And from this set of data here, the top row is the proton density weighted image, and the bottom row is the corresponding flip angle map. You can quite clearly see that compared to the birdcage mode, or that's another name for circular polarized mode, or what we achieve at 1DX systems. Compared to that, the RF shimming and two-spoke system images can achieve clearly more homogeneous flip angle across the whole field of view. So how can PTX achieve this? We start from the system point of view, like the hardware. So for a traditional 1DX MRI system, you would have one amplifier that controls all the transmit elements in the coil. But in a PTX system, each individual transmit element on the coil can be controlled by its own amplifier. Now, what that means is that in a 1DX coil, all the relative amplitude and phases are built in the hardware, in the coil. And for example, if you have an 8-element transmit coil, the phase difference between each transmit element is fixed at 45 degrees. But in a parallel transmit system, the amplitude and phase of each transmit element can be controlled at runtime precisely by the amplifier. Now, what that brings is, of course, the difference in B1 map. And for 1DX system, at higher fields, we usually have a quite significant central brightening effect in brain imaging. But with PTX system, we can achieve more homogeneous field. So having all the hardware, how can we achieve, or how can we design a set of pulse that we desire at the scanner? We usually go through these 4 steps to design a set of subject-specific PTX pulses, and I will quickly walk through what each of the steps involve. Now, first one is you need to define a target magnetization. So most of the cases where we often want to see the desired contrast that we want to see in the subject without any other distortion. So we would like a homogeneous flip map across the whole field of view. And that's done just by setting the flip angle at the scanner the usual way. However, PTX can do something a little bit more interesting. So for example, here we can very precisely and uniformly excite a particular volume in a 3D imaging. And there can be more use cases for that, for example, in spectroscopy and for, say, reducing the imaging time if you are only trying to image a small volume. And on the right here, I'm just showing here, it's also possible to excite the magnetization in a very exotic way that we desire. Okay, having defined our target magnetization, next step, or usually automatically done on the scanner, is that it will run the adjustment sequence where it acquires the field map of both the B0 and the B1 plus for each channel. And that in that step, the scanner is basically collecting information it needs to run the optimization algorithm later on. Afterwards, we need to define a set of trajectories that help to play the PTX pulses. So this is a bit, this may not be very intuitive at first, but if you think about that, the whole concept of MRI imaging is based on the fact that the image is encoded in the K-space. And this is a similar concept, but applied to the excitation. So during the excitation, you will try to move around in the K-space and excite at particular points in the K-space, and that can help you to achieve your desired magnetization. So usually, when you are trying to run the sequence, there will be rather limited choices available in the sequences, and the most common choices is called the spokes, which you move, which does the 2D excitation, and you run it, you move around in the XY plane to some particular points, and you place some pulses there. Of course, if you want to achieve a more homogeneous field, you can increase the number of spokes, but you have also need to take into account that the longer the time it takes, the more the T2 start decay takes its effect. So it's usually a balance between the imaging speed and the quality you want. So that's the second thing the user needs to input. And the last step is also automatically run by the predefined algorithm. And having all the information we have, the algorithm just runs to minimize the target, the difference between the current simulated magnetization to the target magnetization. And this will give us a set of amplitude and phase for each channel to achieve our desired flip angle map. Now, of course, there will be many ways to achieve a similar flip angle map. So what we put in to regularize the choice is to penalize the high amplitude, because that means higher SAR, and we don't want higher SAR in our imaging sequence. So that's the steps to take to design a set of subject-specific PTX pulses on the scanner. And now I'm just going to give you a few examples of what we can achieve, what we have tested and tried in Cambridge. Now, first of all, quite importantly, this is the EPI bolt sequence that's done with PTX. And on the image here, the left and right are formed with the same set of imaging parameters, but we can clearly see that on the right, say in the frontal orbital cortex and the temporal lobe here, the dropout has been significantly suppressed because the PTX pulse can account for these field inhomogeneities in this region. Now, this in a 6-subject visual paradigm study here, we can clearly see that in the circled area, the TSNR with the PTX pulse is significantly increased compared to using the traditional 1TX CP mode pulses. Another example of EPI readout is to do diffusion, and this is only recently been done across a few subjects. And we can quite clearly see that using the PTX mode, the flip angle map we get from these subjects at lower parts of the brain is way better than using traditional CP pulse. And we've done a TBSS analysis here, which is usually done between the patients and control groups. But here we are just trying to show that some of the fractional anisotropy map skeleton in the in the subjects are recovered by the PTX pose, while some are missed out during CP acquisition. And of course, this we have some poses available for structural imaging, and this particular set is called pasture, and it uses a universal pose for structural imaging. Universal pose basically means that we do all our 4 optimization steps beforehand across a number of subjects, and in this case, it's across 20 subjects. And at the scanner, we just place the pose as it's already been defined, so it's a faster way to use PTX. And we can clearly see that the dropouts at the cerebellum area has been improved by using the universal pose. And also in MP2 rage sequence, we can see that on the side of the cerebellum, the dropouts in the CP mode has been removed by using the universal pose. The MP2 rage sequence usually gives us a very important T1 weighted image, and usually in T1 weighted image, the dropouts aren't very obvious because the 2 inversions, when you do the division between them, the 2 inversions will cancel out each other where you have the dropouts. But we can, if we look clearly, we can see probably here around cerebellum area, the signal to noise ratio here, it has been increased through the universal pose acquisition, as we can see a bit more noise in the CP on the left here. So this set of pasture set of universal pose we have in other sequences as well, like MP rage, double inversion recovery, and etc. So that's basically what I'm introducing today. And at last, I just want to say that, as always, we would love to see our developments that can be used in real studies and even in clinical situations. And we're always keen to make that happen through collaborations with other groups. Thank you very much.